I'll do my presentation in English, so I just saw today that I'll probably be the first who does that. So in the lab, I'm from the lab of Dr. Rafael Najmanovich in Université de Sherbrooke. And in the lab, we develop our own molecular docking algorithm called FlexA. And with FlexA, you can predict the binding pose of a small molecule or peptide in complex with a target. It can either be a protein or a nucleic acid. And because docking in general has a relatively short computational runtime, you can apply it to virtual high-throughput screening. And in pharmacology, the method is often used to screen large bank of thousands of compounds to identify initial hits. And that can make you save a lot of money and a lot of time. However, the main issue with docking is that the protein is most often considered as a rigid object when it should be flexible, because proteins are dynamic objects. So previously, we studied one particular type of side chain of protein flexibility, the side chain rearrangements, and we first built a database of bound and unbound structures of the same protein to study the extent of protein flexibility that takes place upon ligand binding. So we studied the nature and the frequency of these changes, and the main findings are that side chain rearrangements are common because they occur in 90% of all binding sites. But they are also crucial because they are critical from a physical point of view about 1/3 of the time. And this result is very important because it tells us how essential it is to include side chain flexibility because rigid docking fails in a large fraction of cases. We also showed that side chain rearrangements are correlated with entropy and rearranged hydrogen bonding. We can turn the lights. And with all the statistics that we derived from this study, we included a probabilistic approach of side chain flexibility in FlexA. And for cases where larger rearrangements of the protein are required for ligand binding, we implemented our NCOM algorithm developed by Vincent in the lab. And with NCOM, we can sample the large conformational space of proteins. And generating these movements is a matter of seconds rather than having to cluster protein conformations from a molecular dynamics simulation. However, this feature is still under development and has not been applied in the results I will present to you later in the presentation. And as a last feature, I also implemented a grid computing infrastructure that allows people from around the world to volunteer and execute computational tasks for us while their computer is idle. And we now have our own project called Energy at Home. And if you want to contribute, you can go to that address. This plot's not very clear, but here's a docking experiment in which we dock thousands of unique peptidic inhibitors against the matriptase. And with this infrastructure, we can dock nearly 4,000 compounds per hour. And so we can do nearly 100,000 compounds simulation per day, which is very a lot. And what we've done here in a couple of days would have taken us months without that infrastructure. So in summary, what we can do with FlexA, we can include all types of flexibility, ligand flexibility, and from minor to major conformational changes of the protein. We can do virtual high-throughput screening with it, and I do not have the time to get into details, but I'm also developing in parallel the Energy Suite, which is a graphical user interface that is integrated into Python, and that allows to use FlexA in a user-friendly manner. And I do not have time also to get into the details of the performance of the method, but if you want to discuss about it afterwards, I would be happy to answer your questions. So we have developed all the necessary tools in FlexA that allows us to apply our method to real biological systems. So we started using FlexA against a variety of targets, such as an enzyme from Pseudomonas, a kinase that's implicated in the triple-negative breast cancer, the human proteases, the matriptase and matriptase 2, and the GPR and ribose switches from Clostridium difficile. And for the remaining of the presentation, I will focus on 2 of these applications. So our initial goal is to help accelerate drug discovery by identifying initial hits and eventually lead compounds. And to do so, we used a fragment-based drug design approach using the Anamine Golden Fragment Library, or EGFL. And the theory behind this approach is fairly simple. You dock and ensemble the fragments into your cavity of your protein of interest to define its binding profile, and then you can generate larger ligands that will be more selective to your protein by combining multiple fragments together or by searching databases. So one of the targets we're interested in is the matriptase-2, which is a member from the TTSP family. And this extracellular protease plays a central role in iron metabolism. And our goal is to target an allosteric site of the catalytic domain to avoid the cross-reactivity among other proteases. And here in different colors are shown the multiple cavities that could be targeted for allosteric inhibition. So we have docked the entire GFL library into each of these cavities, and we have calculated the energy values of the dock conformation using the MMGBSA potential. So we first wanted to identify the hotspots. In which of these cavities do the fragments tend to bind the strongest? And here we use a catalytic site as a reference because we do not want to target this site. And here's the average MMGBSA score for all fragments. And the lower the score is, the stronger the fragments bind to that pocket. And we observe that the preferred binding site is the allosteric site number 5, shown in white here. And here's a similar plot to the one to the left, but this is for an individual fragment. And for the remaining steps, we only selected the fragments that we predicted as being highly selective to our allosteric site of interest, and not elsewhere on the protein. And for this project, we're fortunate to collaborate with the lab of Dr. Richard Leduc, and so we can have experimental validations of our predictions. And activity assays were carried out using the top 10 fragments according to selectivity. And we were really thrilled actually to see that one of the fragments is actually a hit as it reduces the activity of the protein by 22%. And we are now at the step of searching the zinc databases, which is a database that contains millions and millions of compounds that are commercially available. So we are searching for larger molecules that contain our template molecule or fragments of it that we know are important for binding. I'll quickly skip to do another application, another target we're interested in. It is a germination protease from Clostridium difficile, and it belongs to an atypical aspartate protease family. And by targeting this enzyme, we would actually abort the germination process of the bacteria and kill it. So because there are currently no crystal of the GPR from Clostridium difficile, we generated an homology model from the GPR from Bacillus. And our objective in this project is to develop a competitive inhibitor against this protein. So we define the binding site surrounding the two catalytic residues that are aspartates in this case. So we use the same kind of approach than we did for the matriptase-2. We docked the entire GFL library into the catalytic binding site, and we rescored using the MMGBSA potential. And here's a distribution of scores. And here we cannot see the points clearly, but we selected the fragments that we predicted as being the strongest binders. And in the experimental part of our lab, we have purified the GPR, and I've used differential scanning fluorometry assays to calculate the denaturation temperature of the protein alone and in fragments, in complex with the different fragments. And interestingly, all the fragments that we predicted as being the strongest binders, except for one, all have higher denaturation temperature than the other fragments. But with our experience, a variation of 2 degrees using this method is not significant. So we're really looking forward to advancing further in this project using the one-hit molecule that we have identified. And in conclusions, we're gathering more and more evidence that FlexA can really be applied to accelerated drug discovery. We have found hits against multiple targets that we have validated experimentally, despite the fact that the binding of fragments can be quite hard to detect considering their size and the limited number of interactions they can make with the protein. And with the results we have so far with the GPR, we've been able to propose a pharmacophore model of binding just by superimposing the top fragments. And here only the top 3 are shown, but a few interactions were conserved among the top fragments, such as a donor pi or an ionic interaction, and also the covering of a hydrophobic cavity. So what's remaining to do in this project is to combine these fragments together, or parts of it that we know are important for binding. It's kind of like fitting the pieces of the puzzle together. It's exactly the same thing. And also, finally, in perspective, we have developed a method that can account for a wide range of flexibility and that can be applied to a large variety of biological systems. And we want to keep on developing the integration of NCOM into FlexAge because the large-scale movements of proteins might reveal novel cavities that are undetectable if the proteins remain rigid. So we want to apply our innovative method to the detection of cryptic binding sites that could be targeted for allosteric inhibition. And on that, I would like to thank everyone in the lab of Richard Lezuc also, financial support, and you for listening.